Okay, so now we're going to take a look at a few classes of matrices that are particularly nice to work with. And that is the diagonal matrices, triangular matrices, and symmetric matrices. And I'll tell you what all those mean momentarily. So we'll start with diagonal matrices. So a square matrix is diagonal. Here's a new term. If all of the entries not on the main diagonal are equal to 0. So, in other words, if you have a matrix, it's diagonal if it satisfies the following property. If it has any entries that are not equal to 0, they had better be on the main diagonal. Think of it that way. So here are a few examples, or 4 examples in particular. So here we have a 2 by 2 matrix, and this is a diagonal matrix, because you can see there's only 2 non-zero entries, 2 and -5, and they're both on the main diagonal. These entries are referred to as the main diagonal. So what we actually have a notation for this, which I'll write down now. We can write DIAJ, diag, just short for diagonal, and then you can write the entries that are on the main diagonal in the proper order from top left to bottom right, and then that's how you can specify a diagonal matrix. Because think of it this way, if I covered this up and I asked you, what else can I use to cover this up? If I were to cover up where this came from and ask you how can you recover a matrix from this, well, you can count the number of diagonal entries. There's 2. So that means it's a 2 by 2 matrix. Then just simply copy these 2 entries onto the main diagonal and put zeros everywhere else, because you know a diagonal matrix has to have zeros everywhere that's not on the main diagonal. So this notation really does capture the essence of a diagonal matrix, because really, if you know that a matrix is diagonal, the only entries you need to specify are the ones that are on the main diagonal. So that's why we can write a diagonal matrix in this way. Now in this case, it would just be easier to just write down the matrix. You'd probably save more ink if you just wrote this down directly, but for larger matrices that won't be the case anymore. Okay, so here's a 3 by 3 matrix. This is a diagonal matrix. What are the 3 entries on the main diagonal? 1, 1, and 1, right? And everything else is a 0. So it satisfies the definition of a diagonal matrix. And if you wanted to use the same notation, you could write this as diag of 1, 1, and 1. That's how you can specify this matrix using the same notation. Here we have an interesting example. This is a 2 by 2 0 matrix. Is that allowed? Does that count as a diagonal matrix? Well, the entries on the main diagonal are 0. But that's okay. Nowhere in this definition does it say that there can't be zeros on the main diagonal. It's just that if there's anything not 0, it's only allowed to be on the main diagonal. But it's completely fine if the entries on the main diagonal just happen to be 0, as long as there isn't anything else that's off the main diagonal that isn't equal to 1. So this is also a diagonal matrix, and we can write it like the following. We can write it as diag, and then what are the entries on the main diagonal? Well, they're both zeros, right? 0 here and a 0 here. So we just write it like that. And then lastly, you've got a 4 by 4 example. And here's an example of a matrix where not all the entries in the main diagonal are 0, but some of them are, right? So or one of them is in this case. So this is a 4 by 4 diagonal matrix, and we can write it as diag of 6, -4, 0, and 8. And that's all there is to it. So in general, the notation that I'm using, I'm going to jump down here because this is where it just turns out here's where the best place is for issues of room. For notation, the most general way to state the notation I'm using is if I have numbers D1, D2, all the way up to say Dn for some positive counting number n, let's say these are all real numbers, then I can write diag, and then I just write a round bracket, and then I list these numbers, D1, D2, all the way up to Dn, and what that means is the following. It's just this matrix here. Right, I go D1, that's the first entry in the first row, first column. The next entry, D2, will be the next one on the main diagonal, and then I just keep going all the way down to the very last one on the list here, Dn, and that's going to be in the bottom right corner. So I just copy and paste those entries onto the main diagonal, and then you put absolutely everywhere else you'll put a 0. So I'd have zeros all the way down for the rest of this column. Then the rest of this column would also be zeros, and then zeros would go all the way up until I got to the Dn at the end. Then the first row, you'd have zeros everywhere up until the end, and then the same pattern right here. So just copy these entries onto the main diagonal and put zeros everywhere else. And that's all there is to it. That's all there is to interpreting this notation. Okay. All right, so a couple of nice facts about diagonal matrices. The first one is that it's easy to tell when they're invertible. So the matrix diag, and I'll just use the same notation, D1, D2, all the way up to Dn. So this matrix is invertible. Exactly when all of the entries, all the entries in here are non-zero. So D1 is not equal to 0, D2 is not equal to 0, all the way up to the last one, all the way up to Dn is not equal to 0. Okay, so for example, if we just look at these four examples, this matrix is invertible because both of the entries 2 and -5 are non-zero. This one's invertible because all the entries are non-zero, right? In fact, this is the identity matrix. We know that the identity matrix is invertible. The zero matrix, this 2 by 2 zero matrix, we know that's not invertible, but here you can look here and you can see that just because some of the entries here are equal to 0, well, they both are in this case, but even if as soon as a single one of these entries is equal to 0, the matrix is not invertible. And then same with this one over here, right? Because of this 0 here, this matrix is not invertible. That's what this fact is saying. And the second fact, in this case, so in other words, when it is invertible, we can write down the inverse as follows. Just write that the inverse of the diagonal matrix that I've written down here is just equal to the following diagonal matrix. Just take the reciprocal of each of these entries on the main diagonal. So you're going to have D1 inverse, D2 inverse, all the way up to Dn inverse. And that's your formula for computing the inverse of a diagonal matrix. And of course, this is guaranteed to make sense over here because these reciprocals, you don't run the risk of, well, what's the one number you can't take a reciprocal of? And that's the number 0. But we're talking about in the case when all the diagonal entries are not 0. So right, we're talking about this case. When all the diagonal entries are not 0, you can use this formula to get the inverse. But if a single one of those diagonal entries is 0, well, then you wouldn't ever apply this formula because we already know, based on the first fact, that you would have a diagonal matrix that's not invertible. Okay, let's look at a couple of examples of that, see it in practice. So here we've got a 3 by 3 matrix. The diagonal entries are 1, 4, and -3. So if I want its inverse, which I've written here, well, based on fact 1, this matrix is invertible. So it makes sense to put this inverse symbol up here in the first place because all 3 of those diagonal entries are non-zero. So what are we going to do? Just write down the inverse, and we'll just take the reciprocal of each of those entries. So the reciprocal of 1, just 1 over 1, is just going to be 1. The reciprocal of 4, 1 over 4, well, that'll be 1 over 4. So that's an entry right there. The reciprocal of -3, that's going to be 1 over -3, or in other words, -1/3. So those are the entries on the main diagonal of the inverse of this 3 by 3 matrix. So let's fill in the rest now. We have zeros everywhere else. And there we go. So that's the first one. What about this 2 by 2 matrix here? I didn't even write the inverse symbol here because I'm not even going to go that far, right? Because one of the entries on the main diagonal, namely the one I'm pointing at right now, is 0. So based on the first fact, this matrix is not invertible. So that one we won't even start talking about the inverse because it doesn't make sense to. And then for this third example, well, this one is invertible because all 4 entries on the main diagonal are not equal to 0. So we can go ahead and write down the inverse as follows. Just take the reciprocal of every entry. So we got 1/9, 1/3, 1/2. And what's the reciprocal of -1? 1 over -1 is just -1. So actually, -1 is its own reciprocal. And then again, we're going to put zeros everywhere else. Okay, so that's all there is to it. Finding the inverse of a diagonal matrix is really nice. You don't have to do the inversion algorithm or anything. You just need to be able to take reciprocals of diagonal entries. And if any of them are 0, stop. The matrix isn't invertible. It's fairly straightforward. So that's why I mentioned that this is a section where we're going to look at types of matrices that are particularly nice to work with. And that's not the only reason that diagonal matrices are nice to work with. Computing powers of diagonal matrices is actually very convenient as well. And because remember, computing powers of computing powers of matrices is very cumbersome because powers are repeated multiplication, and multiplication of matrices is very cumbersome. So we would typically expect computing a large power of a matrix, like this one here, for example, down here in the example on the right, you're raising a 3 by 3 matrix to the power of 4. Think about what that would entail. You'd have to multiply this matrix by itself, then multiply it on again, then multiply it on again. You'd be doing 3 products of 3 by 3 multiplication. Just to compute this power. And 3 by 3 multiplication is no joke. But it turns out there's actually a really nice rule for computing this as well. So let's say we had some positive counting number k, just to act as an exponent. Then if you want, here's your rule. I'll say then, if I want to take the diagonal matrix d1, d2, all the way up to dn and raise it to the power of k, well, then all I have to do is say this is the diagonal matrix with diagonal entries, d1 to the power of k, d2 to the power of k, all the way up to dn to the power of k. Okay, and that's all there is to it. If you want to raise a diagonal matrix to a power, just simply raise all of the diagonal entries to that power. Okay, and that's really nice. That's not how you raise a matrix to a power in general. This is very, very nice that it works out this way for diagonal matrices, but don't expect this to work for other types of matrices. But let's look at a couple of examples of applying this here. So I've got a 2 by 2 matrix, 9, 0, 0, 11. I want to raise this to the power of 2. I just have to raise both of the diagonal entries to the power of 2. So if you raise 9 to the power of 2, you get 81. And then the zeros will stay as zeros, and then 11 squared, if you remember your times tables that high, you get 121 for that. So that's what you'll get, right? So that's all there is to it. I don't have to do matrix multiplication. I just need to apply those exponents directly to the entries in the main diagonal. Okay, one more example over here. I got a 3 by 3 matrix, and it's a diagonal matrix, and I want to raise it to the power of 4. So I'll raise each of these entries to the power of 4. So 2 raised to the power of 4 ends up being 16. Negative 3 raised to the power of 4. Well, negative 3 times negative 3 is positive 9. So negative 3 to the power of 4 is really just 9 squared, which is going to give us 81. And then negative 1 raised to the power of 4 is positive 1. So then I'll have zeros elsewhere. And then I can fill it in like that. So finding the inverses of diagonal matrices whenever possible and computing powers of diagonal matrices is very convenient, and it's quite easy to do compared to other matrices.